This is section 4.4 in the textbook on families of functions. So let's start out with a very simple example. Let's consider f of x equal to x squared. And so I'll just sketch a rough sketch of it. And then let's consider using two parameters to translate the graph to where we want it to. So if we consider number 2, f of x equal to x minus h squared plus k, by replacing the input variable x with x minus h, if h is greater than 0, this will translate the graph to the right h units. The k, on the other hand, is added to every y value. So if k is greater than 0, the graph is translated up k units. So that's the vertical translation. So in this case, if they're both positive, the vertex would move h to the right and up k. So the vertex would move up here, and it would translate every point in the parabola in the same way. And so it just moves the parabola to a different position. This is one use of parameters. Parameters are constants. We give them a letter because we don't know beforehand what constants we might assign to them. It depends upon the application, or in this case, where we wanted to translate the parabola. Notice that in this particular example, if h were negative, say we had y equal to x plus 2 squared minus 3. So in this case, both h and k are negative, and this would translate it 2 units left and 3 units down. So that's one use of including parameters in the expression for a function. Now we could graph the standard parabola by plugging in many values for h and k, and this would give us what the book is calling a family of functions. So we'll see more of that below. But first, let's experiment with our graphing calculator. And let's see how it can graph a family of functions for us. So if you take out your graphing calculator and you go by these instructions here, and you hit the Stat key, and then Clear List, select Clear List, and then do Second Stat, and select L1, and enter that, then this will clear any values that were in list named L1. If you now do what's in the second line on your graphing calculator, hit the Stat key, and then select Edit, you'll see the 3 lists listed in the screen of your graphing calculator. Then just it's automatically places the cursor in list 1. So type 0, enter, 1, enter, 2, enter, and this stores the values 0, 1, and 2 in list 1. So if you need to pause this video and do that, go ahead and pause and do that. And while you're doing it, in for y1, go to your y equals, and in for y1, type in open parentheses x minus, and then go to your list second stat, which is your list menu, and select L1 again. That will place L1 after the minus sign, close parentheses, and square. So we have x minus L1 squared is in y1. Notice that the different values in the list are just going to provide different horizontal translations to the standard parabola. And we'll start with the standard parabola because 0 is going to be our first value that it plugs in here. So first, the graphing calculator is going to graph x squared. Then it will take 1, the next number in the list, and it will graph x minus 1 squared. And then it will take 2 and plug that into the list from the list into the expression and graph x minus 2 squared. In this way, your graphing calculator will graph the family of functions determined by the parameter values that we've stored in list 1. So in order to graph it, let's choose a common window. Put -2 for x min, place 5 in for x max. You can put a scale in of 1 if you wish, or turn it off, it doesn't matter. Put 0 in for y min and 6 in for y max. So go ahead and pause your calculator if you haven't done all that, and then come back to the video. And then when you've come back to the video, go ahead and select graph and graph this family of functions. So what you'll find is you'll see it graph first the standard parabola x squared. Next, it will graph the parabola x minus 1 squared, which just translates the standard parabola 1 unit to the right. And finally, it will graph y equal to x minus 2 squared. And so you see your family of functions on your graphing calculator screen. And you could graph more families, more functions in that family just by putting more values in your list to substitute in for that horizontal translation parameter. So this is what your book means by a family of functions. Okay, so let's consider a family of cubic functions. So I'm going to use a parameter a, and we see in expression or the equation for 3 how we're using the parameter a. We have x cubed minus ax, and to the right I've already graphed my function y equal to x cubed. We're going to use the same list. It's already in your graphing calculator, and so I want you to go to y equals in your graphing calculator, and then for y1 I want you to clear out the old y1, and I want you to put in x cubed minus L1 times x. And remember how to get L1 here. You have to go to second stat and choose L1, and it will bring it back and put it in after the minus sign. Okay, we already have the values 0, 1, and 2 stored, and now graph. Let's see. Let's change the x min and x max. Let's change the x min to -1.5 and x max to 1.5. And then let's zoom fit. Let's let the calculator determine the y values that we need to get those graphs on the graphing calculator screen. So if we do that, you'll see y equals x cubed, and then you'll see the next one should be x cubed, y equal to x cubed minus 1 times x. So that one will look like this. It actually has a local max and a local min now. And then the next one your graphing calculator is going to graph is y equal to x cubed minus 2x, because that is the next, or that is the last number in the list L1. And when your graphing calculator graphs it, it's going to look like this. So the max and the min will be more pronounced. As a matter of fact, each time the min and the max is going to be moved a little bit. And so the mins are going to move to the right and the maxes are going to move to the left as the parameter value a increases. You could put more values in your list, like 3 and 4, and you would see the cubics would do what we think they're going to do. The min and the max are going to spread further and further apart and become more and more pronounced as the parameter a increases. And so we can get a good idea about what that family of functions actually looks like. So I'm going to go ahead and, for the answer here, what effect does the parameter have on the graph as a increases? I'm going to say that the local min and max move further apart. Now it wants us to verify using some paper and pencil calculations what we just observed. So we could do that by, we know the local min and max are going to occur at critical points. So we go ahead and we take our f prime. So f prime will be 3x squared minus a. Set that equal to 0 and solve for x. So x is plus or minus the square root of a over 3. So if we do a sign chart here, put our two critical points on the number line, I can determine the sign of this derivative. If I plug 0 in, then I get negative a. So we're going to take a to be a positive value, so the derivative is going to be negative. The graph is going to be decreasing between the two critical points. If you choose a value greater than the square root of a over 3, then, let's see what happens. Maybe 2a, square root of 2a over 3. So I have 3, the square root 2a over 3 squared minus a. And so it's 3, 2a over 3 minus a. So it's 2a minus a, or a. So this is greater than 0. So I've chosen a point out here, square root 2a over 3. I plugged it into the first derivative, and I got a positive number. And likewise, you'll get a positive value for the first derivative over here. So this is where we're observing our local maximum in the cubic over this critical point, and the local minimum we're observing here in the cubic. And we can look up at that family of functions and we see that. And now as the parameter a increases, this point is going to move to the right, and this critical point is going to move to the left. And that's going to move those max and mins further apart. So we have verified using a paper and pencil calculation what we've observed in the family of functions using our graphing calculator. Okay, so let's look at the a specific example. In this case, in equation 4, we're going to look at s of t, which represents a position function for an object moving vertically only under the influence of gravity. So we have parameters a, b, and c, and these values may specify or represent different physical conditions or constraints or physical values in the application. And normally, since this is a function of time, we can tell what those parameters actually represent. So that if I plug 0 in for time, I get s sub 0, and the first two terms go away, and I just get c. So s sub 0 equal to c. Well, s sub 0 is the vertical position at time 0. So sometimes we will represent that parameter c by the symbol s sub 0 for initial position. And notice if we take the derivative of s prime, we get 2at plus b. So this is the velocity. The time derivative of position is velocity at time t. If we then plug 0 in for t again, we get s prime of 0, and the term 2at disappears because t is now 0, and we just get s prime of 0 is b. This is the velocity at time 0. Sometimes we will represent this by v sub 0, and we call it initial velocity. So we have an initial position is c, initial velocity is b, And finally, if we take the second derivative of position, this is acceleration at time t, we get 2a. So we're just taking the derivative of s prime up here, and we're getting 2a. Notice this is a constant function, and so this corresponds to the acceleration of gravity. So we write 2a equal to negative g. We can include the negative sign because we assume gravity is acting in a downward, the acceleration is acting in a downward direction. So that's where the negative sign comes from. We're going to take the upward direction to be positive, and we give it the symbol g because it depends upon what body we're talking about, where we're at on the Earth, if we're talking about the Earth or we're talking about the surface of the Moon, as to what the value of g actually is. So if I solve for a, I get a is minus g over 2, and then I substitute all my representations of the physical quantities back into my expression for a, b, and c, and this is what my vertical position function looks like. Negative 1/2 gt squared plus b naught t plus s naught. So that should look familiar to you. You've probably seen that before. We might have even looked at it earlier in this course. And once we have this, we can fill in different values for the parameters. But what I want you to recognize with respect to this section is that that is indeed a family of functions. Depending upon the different parameter values that we plug in, which will depend upon the different physical conditions under which we're using our vertical position function. So let's take an example. What is the equation of the vertical position for an object near the surface of Mars where the acceleration of gravity on the Martian surface is 3.8 meters per second squared? The initial position is 30.4 meters above the surface, and the initial velocity is 11.4 meters per second upward. Okay, first of all, the g on Mars is 3.8. So negative g over 2 is negative 1.9 times t squared, and then we put the initial velocity next. That's 11.4 times t, and the initial position is 30.4. So that would be the equation of vertical position for this object near the surface of Mars, starting with the under the conditions that we've specified. Then we can answer questions. Once we filled in the parameter values, we've chosen now a specific member of the family, and having chosen those values, we can answer how long until the object hits the Martian surface. So it's going to hit the Martian surface when the vertical position is 0. Notice the unknown here is time. So if I take and set this quadratic function equal to 0, I've chosen the values so that this quadratic equation would be easy to solve. If we divide both sides by 1.9, by negative 1.9, I get t squared here, the first term. 11.4 divided by negative 1.9 is, let's see, I did that already, minus 6t. And then 30.4 divided by negative 1.9 is negative 16. So I chose the values so that we could factor this, so we might get t minus 8, t plus 2. And so we get two solutions to this quadratic equation, negative 2 and 8. And we're not going to talk about what happened before the experiment began, so we're going to ignore the negative solution. And so we get 8 seconds. 8 seconds after the object is released, it would hit the Martian surface. So what did it do? Let's see, it started up here at 30.4. Here's the surface. Started right here. It was headed that direction. It went up. and came back down and took 8 seconds to hit the surface. Okay, let me, erase this. Sorry about that. How high does the object travel above the surface? So how high does it go? So that's going to be, if I look at the picture, where it reaches this peak. So at that point, the velocity is going to be 0 because it's going to be turning around. So if I just find the velocity, it's the derivative of position, that's minus 3.8 t plus 11.4. So just take the derivative of the position function. When the velocity is 0, that should be when it reaches its highest point. So I get what? 3.8 t equal to 11.4. So t is going to equal to 3. So 3 seconds after it's released, it is moved up to this highest point. So to find out how high it is, I now need to take that 3 and plug back into the position function, the vertical position function, and it will tell me how high it reached. So you should try this, and when you do, you get 47.5 meters. Okay, so we'll be answering questions from our models as well. The important thing that we're doing in this section is trying to learn to understand how to choose parameters that will fit a particular application, and to understand that what we're doing is we're choosing a specific function from a family of functions. So let's do one more. This is example 5 in your text on page 219. The number n of people who have heard a rumor spread by mass media by time t is modeled by this function. N of t is equal to a times a quantity 1 minus e to the minus bt power. Okay, so we want to fit this model to this particular situation. There are 200,000 people in the population who will eventually hear the rumor, and if 10% of them heard by the first day, find the values of a and b, assuming t is measured in days. Of this population of 200,000 people who are going to eventually hear the rumor, that would be all the people who ever hear the rumor. So that's going to be the limit as t goes to infinity of n of t. This is going to be my 200,000. The total number who ever hear the rumor. So what I can do is now take the limit as t goes to infinity of my expression, a times 1 minus e to the minus bt. Now this power up here is negative because I have a negative in front of the b. So as time goes to positive infinity, the power goes to negative infinity. So if I have an exponential raised to a power that's going to negative infinity, this term will be approaching 0. And so I'm only left with a times 1 in the limit. So therefore the parameter a represents the total number of people who will ever hear the rumor. So we're going to substitute that value in for a into our model. And then to get the value for the parameter of b, we're going to use the data point. It says that 10% of them heard by the first day. So 10% of what? 10% of the 200,000. So 20,000 had heard by the first day. So if I let n be 20,000, at time 1, I just set up an equation now and I solve for my missing parameter. So I have what? N of 1 is 20,000, and n of 1 is also equal to 200,000 times 1 minus e to the minus b times 1. So now I just have an algebraic equation where b is my unknown. So I divide both sides by 200,000. and I subtract 1 to the other side, and so that will give me negative 9/10. So I'm going to have negative e to the minus b is equal to negative 0.9. And now I'll let you solve for b, but you're going to have to, after you multiply through by negative 1, you're going to have to take the natural log of both sides. And you have negative b on the left side, and the natural log of 0.9 on the right side, and you can solve for b and get a numerical value. When you do, you're going to get, I think, here's my calculator, let me go ahead and do it. Natural log 0.9, and we're going to get b equal to 0.10536. So I have a is 200,000, b is 0.10536. So when I assign those parameters to a and b, I now have one member of the family of functions determined by those two parameters a and b. And that member will answer, that function that I just chose, will answer questions about the spread of this particular rumor. So you can ask questions like, how long did it take for 100,000 people to hear the rumor? So you can ask questions about time. You can ask how many heard the rumor by a certain time. How long did it take? Or you could ask like, how many people have heard the rumor by 100 days, and so forth. Okay, well, your exercises give you some more examples of fitting a family of functions, fitting the parameters in a family of functions to specific problems. It asks you to look at what happens to local max and mins as different parameters in a family of functions varies in some way. And so if you'll work the recommended exercises that are on your homework schedule, then we can pick up here and discuss families of functions again when I return. Okay, bye-bye.